Hi there. Welcome to Eduretics, where we make your high school life simple. I'm Aniket, and this is the next part of our functions and graphs video series on our mathematics concepts playlist. So in this video, we're going to discuss transformations of graphs. So in the last two videos, we've seen how to analyze the functions, their graphs. In this video, we're going to see how to transform according to some given changes, some given conditions. So this will give you an edge in speed while you solve questions on the test. Okay, let's begin. The first kind of transformation that we're going to discuss is, let's say you have y is equal to f of x, and we go for y is equal to k times f of x. Okay, so it's really important to understand that there's a difference between y is equal to k times f of x and y is equal to f of kx. Okay. In one of these, in the top one, we're changing the whole function, we're transforming the whole function, while in the bottom one, only the x is getting changed, the input is getting changed, it's getting scaled by a factor of k. Okay, so for example, let's put this into context. I take y is equal to, let's say x squared. Okay, this is a simple quadratic equation. When you draw it, when you draw the original function, it'll be something like this, touching the origin. The vertex is at the origin, since minus b by 2a is the x coordinate of the vertex, and the b here is 0, which is basically the coefficient of x. That's 0 here. So here's the vertex. This is the original graph. Now you're given k times fx, this transformation, that this becomes kx squared, or let's say 3x squared. What happens? It'll accelerate the graph. For example, at x is equal to 1, initially fx was 1. Now at x is equal to 1, new fx, or let's say f new x, I'm writing, the kfx or the 3x squared, according to that, it'll be 3. For x is equal to 2, earlier it was 4. Now it'll be 12. Okay, so you see a rapid scaling. So these things would shrink, the arms would shrink with the increase in the value of k. Okay, it'll keep on shrinking as you keep increasing the k, and it'll keep come really close to the y-axis with almost vertical growth as the k becomes higher and higher. Okay, so this is basically a vertical shrinking, you can say. Okay, it's scaling, but in turn it gives you a shrinking. So higher values come at like really lower values of x, higher values of y come at lower values of x. Okay, this is the first transformation. You can call this as vertical shrinking. Okay, so we did y is equal to k times fx. The whole function was scaled. Next, let's see the other one, the one I've written just below it. Okay, so you had y is equal to x squared. Now you're doing y is equal to f of kx. So it's getting changed. The x itself is getting kx. So let's say it goes from x to 3x. So the new function is going to be y is equal to 3x squared. Okay, this won't be much different from the kind of transformation we saw just now. That is because of the nature of this graph, nature of the quadratic function. So I'll take another function to show you this one. Although it's one and the same thing, like the x would be sped up. So for example, earlier what was happening for x is equal to 1, let's say at x is equal to 1, you had y is equal to 1. Now at x is equal to 1 by 3 itself, you will have y is equal to 1. At x is equal to 2, you had y is equal to 4. Now to get this, you'll at x is equal to 2 over 3 itself, you'll get y is equal to 4. So the graph has sped up. If you see, earlier if it was like this, now it has sped up. Everything's happening faster, quicker. So the same kind of transformation I'm showing on the quadratic itself is the same kind of transformation. Since the graph is speeding up, so it'll shrink. On both sides it'll shrink. So higher values of y on lower values of x, because the x itself has been scaled up in the function. Okay. A more evident version of this can be seen here. So let's take this graph. The best example for this would be trigonometric functions. Let's say you have y is equal to sine of x. Okay, initially with no change the graph is going to look like 0, pi by 2, pi, 3 pi by 2, 2 pi. Okay, and it goes from -1 to 1. Okay, this here is the sine curve. It continues on both sides. Okay, the moment you do y is equal to sine x, you transform it to y is equal to sine of 3x. Okay, sine of 3x. Now what happens, earlier, or let's say we take 2x for simplicity to show you the example. Sine of 2x, what would you do to this graph, to the existing graph? See, at x is equal to 0, what was happening? Sine was going to 0. That will still be the same. But at x is equal to pi by 2, sine was going to 1. Now, at x is equal to pi by 4 itself, sine will go to 1. Why? Because that's a 2x. Okay, 2 times pi by 4 would still give you a pi by 2. Okay, so at pi by 4 itself, at half of it, it's happening, like everything's happening at half of what it used to be earlier. So at pi by 2, at x is equal to pi by 2, what will happen? This is 2x. 2 times pi by 2, it's a pi. Sine will go to 0. So whatever was happening on pi is happening at pi by 2. So you see the period of the function is also reduced. The new function, if I draw it on the same axes, the transformed one looks like this. Okay, so in the same interval from 0 to pi, earlier half the period was going. Now the complete graph is, the graph is completing its period in 0 to pi. Okay, so also from here you can get an important rule that whenever there's a trigonometric function, let's say sine of x, cos of x, or tan of x, anything. So if it's sine of kx, the period, time period becomes t over k, where t is the original period. So for sine it's 2 pi, so 2 pi over k it becomes. So in our case 2x, k is 2, that means 2 pi over 2, or simply pi. Pi is the new period. Initially it was 2 pi. So you see the graph sped up. Okay, period reduces to half. So this is the transformation for scaling. So it will shrink horizontally. Okay, shrink horizontally, or it will increase vertically whenever this kind of a scaling is there, like f of kx or kfx. Okay, I might have said vertical shrinking a few minutes before. I was wrong there. It's horizontal shrinking. It's shrinking horizontally, it's increasing vertically. Okay, it's rising vertically. So this is one of the transformations. This is done. The next transformation which we see is, you have f of x, it goes to f of x plus a. Okay, the input is changing by a units. Correspondingly, for function level, what will we have? We have f of x plus a. Okay, these are two different transformations. This is the input level transformation. You can remember it like this. This is the input level transformation. This is the function level transformation. This is the function level. Okay. So let's see the first one, the input level transformation. For that, say you have y is equal to 3x plus 4. Okay. Y is equal to 3x plus 4. Let's write a data table quickly. X is equal to 0, y is 4, x is equal to 1, y is 7, x is equal to 2, y is 11, x is equal to 3, y is equal to 13. This 3 is 9. This would be 10, and this would be 13. Okay, so this is a quick data table. Now let's draw the original graph. Y is equal to 3x plus 4. The y-intercept is at 0, 4. This is here. X-intercept, that means when y is 0, it's negative 4 over 3. You can see the graph here. Let me scroll a bit. Okay, x is when y is 0, x is equal to negative 4 by 3. So this is 0 comma 4, the y-intercept, and then this would be the x-intercept. So the graph goes like this. This is a straight line. Excuse my drawing. So this is a straight line, y is equal to 3x plus 4. This is the original graph. Now you're given the transform from x to x plus 3. Okay, so a is 3, x to x plus a we're going. So this input, it'll change to 3 times x plus 3 plus 4. Okay, so how do we do this transformation quickly? When you do x as x plus 3, so earlier what was happening on x plus or x is equal to 3, let's say whatever was happening at x is equal to 3, now with the new input, where will this correspond to? It will correspond to x is equal to 0, because when you put x is equal to 0, this would still be a 3, so it will give the original value of 13 for the function. Okay, whatever was happening for x is equal to 4 will happen for x is equal to 1 now, because when you put x is equal to 1, this input will be a 4, the input itself would be a 4. So again you see speeding up of the graph. Okay, so the graph will shift towards the left. Okay, everything will happen earlier to how it was happening before. Okay, so let's say this value, this is negative 4 over 3 comma 0. This is the x-intercept. Now where this function will cut the x-axis, you can check directly. Put y is equal to 0. So let's say this is 0. Negative 4 over 3 minus 3, because x plus 3 is equal to negative 4 over 3. If you just shift this to the other side and bring the 3 down. Okay, so x is equal to negative 4 over 3 minus 3. Now the new x, that means it's shifting towards the left. That's pretty evident, and it's also evident from our logic, the one I gave you, that the graph speeds up, so a units to the left. By how much is it shifting? It's shifting by 3 units, as you can see, and 3 is the value of a, which we changed here. So the new graph will look like a shifted one, and it will be like this. This gap would be 3 units. Okay, this gap is going to be 3 units. Okay. So this is the transformation. So whenever you have something like x going to, or let's say f of x going to f of x plus a, remember this rule, write it down somewhere. This is, the graph will shift a units to the left, a units to the left. Okay, and likewise whenever you have f of x goes to f of x minus a, it'll go a units to the right, shift a units to the right, it'll slow down, the graph will slow down, a units to the right. Okay, here I'm considering a to be a positive number, so change accordingly. Okay, don't memorize this, change accordingly, you just need to understand. So a here was positive, a was greater than 0. Okay, so that's the thing. Next we look at the other transformation, which is the function level transformation of the same thing. So right now what we did was input level transformation, f of x goes to f of x plus a. Now we're going to do f of x goes to f of x plus a. Okay, in this case what happens, so here the transformation happened on the x-axis. If you see, the motion of the graph happened on the x-axis. So I can write here, graph moves on the x-axis. Now in this case, it'll be pretty obvious, since in the input level it was moving on the x-axis, now it'll move on the y-axis, moves on y-axis. This is simpler than the other ones. As you can see, let's say y is equal to x squared. This is, the original one looks like this. The moment I do fx plus a, that means y is equal to x squared plus 2. This is the transformed one. Okay, I'm making the arrow marks for that. This plus 2 is getting added. This means shift the graph 2 units up, simply 2 units up. Whatever value you were getting, now you will get 2 units higher than that. X is equal to 0, y was 0, now x is equal to 0, y is 2. X is equal to 1, y was 1, now it will be 3. X is equal to 2, y was 4, now it will be 6. So everything moved up by 2 units. Okay, so this is simple. Whenever you have f of x plus a, so fx plus a, so shift a units upwards. Okay, and whenever you have f of x minus a, shift a units downwards. So transformations are really important for tests on which you're not directly allowed a graphical calculator, or if you want an edge in speed, because mostly when you have the transformations on your fingertips, you might not even need to check your graphing calculator for each question. So for questions where it's those like there are direct questions on a certain transformation, let's say a units up or a units left, in that case you really need to spend time on your graphing calculator. You can directly do using transformations. Okay, so that's why I'm teaching this. Otherwise for tests where you allow Desmos and all, it'll be fast with Desmos. Yeah. Okay, also the transformations, these strengthen your conceptual understanding. You can anyways go to Desmos or any graphing calculator and check the graphs directly, but this will enhance your understanding. Okay, let's look at the next transformation. Okay, the next set of transformations is y is equal to f of x goes to f of negative x, and correspondingly for the function level transformation, negative fx. Okay, so for this one I'm going to take an example of the exponential function. So I can show you a wide variety of different transformations in each function. So whatever transformation rules I'm telling you, these would be applicable for any function throughout. Even though I'm showing you examples of exponential or quadratic or something, but for each transformation, it will be applicable on each kind of functions. So let's do y is equal to e raised to the power of x. The graph looks like this. Okay, since e is positive. Let's say we take y is equal to a raised to power x. A is any positive number and x is positive. It'll always go like this as long as a is positive. Okay, so on the negative x, it begins from approximately 0. On the positive x, it goes all the way till infinity. Okay, now we transform this to a raised to power negative x. The moment x goes from x to negative x, what happens? You take a mirror image about the y-axis. Okay, I'm writing that clearly. A raised to power x goes to a raised to power negative x. Take mirror image on the y-axis. Mirror image about y-axis. Okay, so the new graph, the transformed graph, would look like this. Okay, no confusion at all in this. Simply whenever you see the input, the x input getting converted to negative of it, take mirror image about the y-axis. You can also remember this as a shortcut, like whenever x is turned to negative x, take mirror image of the y-axis. Whenever y is turned to negative y, take mirror image about the x-axis. So this, the second rule I told you for function level. Y turned to negative y means fx turned to negative fx, this one. For this, you take mirror image about the x-axis. Mirror image about x-axis. Okay, let's see this one, the second case. So y is equal to a raised to the power of x. That graph is like this. Now you transform to y is equal to negative a raised to the power x. Immediately you will take the mirror image about the x-axis. The function goes like this. Okay, this is the transformed function, this transformation. Okay. Now let's take a more complicated example. Let's combine both the transformations. In the single function, we'll do input level transformation as well as function level. So y is equal to a raised to the power of x. Let's transform this to negative a raised to the power negative x. Okay, so we'll do this in sequence. First, sketch a raised to the power x Okay, now to do a negative a raised per x, let's do negative a raised per x. So I'm showing you the sequence. First I do a raised per x, then I go to negative a raised per x. How do I do that? I take mirror image about the x-axis. This is negative a raised per x. Now I do negative a raised to the power negative x. So I take mirror image about the x-axis, y-axis now for the graph I obtained in the second step. So now it will be like this. This is negative a raised by negative x, and this is how you go with transformations in step by step. Okay, this will enhance your understanding. Okay, like why did you take the mirror image in the first place? You could go by another sequence. You could go a raised by x goes to a raised by negative x goes to negative a raised by negative x. How would that look? Let's see. You can try it yourself as well. So a raised by x, a raised by negative x, I take the mirror image like this, then negative a raised by negative x. So I already have this. The negative of this whole function would be a mirror image of the y-axis. Yes. See, we're getting the same thing, this one and this one. Okay, this is done. This is clear. This was another important set of transformations. Let's go for the next one. Next is the transformation to absolute value function. So given y is equal to f of x, you turn it into f of mod of x, or absolute value of x, and correspondingly for the function level transformation it will be absolute value of fx. Okay, this is input level, this is function level. Let's look at these transformations. So as a concept, whenever you take the absolute value of something, the output will always be a positive value, irrespective of whether the input was negative or positive. So conceptually, since you're doing an absolute value of x, the input, whatever input you give, negative or positive, it will act as a positive input always. So for example, let's say y is equal to x squared minus 4. Okay, so this is basically x minus 2, x plus 2. The roots would be at plus minus 2. Okay, so minus 2 and plus 2, like this. Okay, so in this one, okay, let's take a bit skewed one, that'll be better. So I'm taking the log function, that's better. Okay, or let's take another log one, but okay, let's continue with exponential function. You'll soon get to know why I'm thinking so much about which function to take, so as to clearly show you what happens when you do f of mod x. So y is equal to e raised to the power of x. The function looks like this. Okay, in the negative x range it's starting from 0. In the positive x range it's going up to infinity. Okay, the moment you do e raised to the power mod of x, you basically copy the graph on the right hand side of the y-axis, like the positive x graph on the negative x graph, because the input, even if you give x as negative 1, it's coming out as positive 1. Okay, so whatever's happening on the positive x side will happen on the negative x side as well. So you see, this is the graph of e raised per mod x, or absolute value of x. Whatever's happening here, the same values will come here, because x is equal to negative 2. Earlier it was giving e raised by negative 2. Now it's giving e raised by positive 2 only. So it's acting like a quadratic curve now. Like for every pair of positive and negative x, there would be a single value of y. Okay, so that's what we can see here. This value belongs to both. Okay, so whenever you have this kind of transformation, fx goes to f of absolute value of x. That means you take the part, you copy the portion on the positive x side over to the negative x side as well, and keep both the portions. Okay, and the portion on the negative x side which was there earlier, which will no longer stay. Okay, and now for the function level transformation, f of absolute value of fx to absolute value of fx. For this one I'll show you the log function. For better illustration, y is equal to log of x. If you see the graph, it looks somewhat like this. Yeah, basically the mirror image of this exponential curve. Okay, whenever you have mod of fx, what does this mean? This means this value is going to be always positive. So simply whatever portion of the graph or of the original graph is in the negative side, okay, like this one here is the negative side, take mirror image of this portion over the x-axis. So it becomes like this. This is the graph. This is mod of log x now. This one. Okay, this is mod of log x. Now here the quadratic looks really good. So let's say y is equal to x squared minus 4. This will give you a graph minus 2 plus 2 and minus 4. It's going to come like this. But the moment you do y is equal to mod of x squared minus 4, the complete thing, absolute value of the complete thing, the graph positive side will remain as it is, the positive y. This portion of the negative y gets flipped over and looks like this. This is the green one, this is the graph. Now, okay, forget about the negative side y, okay, the bottom one, that goes away. Okay, so this is the absolute value transformation. You can apply it as it is on any function given. Okay, so why we didn't do this one like a f of mod x on this quadratic x squared minus 4? Because x square anyways will give always positive values. Whatever x you give inside, negative or positive, x square is going to be positive. So even if you put mod of x squared is the same as x squared, since the square is doing the action of the mod already, or the absolute function already. Okay, so I hope you've understood this clearly, the transformations. You can keep applying them here and there. This will speed up your understanding. Whenever you get a question which can be done directly using transformation, like there's a minor change in the original function. For example, you're getting something like log of x plus 4. So you directly know that, I'll draw log of x and then raise 4 units up, raise the graph 4 units up. That's simple. Okay, so you can apply such tricks. This will speed up your progress. Stay tuned. We'll be out with the next video soon. Okay, thank you. Take care. Bye bye. Like, share, and subscribe.